Hey, I'm Rage. Welcome to my channel. Let's create an unsigned int 24 type. We start today in OneNote, and this is for me to show you how we're going to plan our type. Our type will be a struct we call unsigned int 24 type, or T. It will have one data member of a std array of 3 unsigned int 8 keys, and we will consider endianness if we have little endian. Then we will have the least significant byte at index 0 of our array, and the most significant byte at the last index. And for big endian, we will do the opposite, right? We will have the most significant byte at index 0 and the least significant byte at the last index. In order to perform operations with our type, we will be initialized from an unsigned int 32 type as the next larger one, and we will implicitly convert to an unsigned int 32 type. The only thing that we have to do then is we have to override all assignment operations. And so on, right? That should be it already. Later down the road, we will specialize std numeric limits for our type, and then we should be done. Let's have a look how we do this in code. So we said already that we will create a structure unsigned int 2014. We will have a data member, which is going to be a std array of 3 unsigned integers. And then we said that we will by default be initialized from an unsigned int 32 type somehow, and we will implicitly convert back to unsigned int 32. But how do we do this now? So what we first do is we default initialize our array. In order now to get a proper representation, we will or we would want to wrap the input data around our maximum value, right? And in order to do that, I will create a static const expr. Let's have it an unsigned int 8, no, unsigned int 32, of course. And this will be our maximum 256 to the power of 3 minus 1. This is the maximum range of our 24-bit integer. If we now wrap, we will have to take the max plus 1 to get a value that is again within our range. We wrap around the input, and then we need to assign our unsigned int 32t, which by now has its most significant byte 0, because we wrapped around a 24-bit representation of a number. Therefore, the wrapped unsigned 32 has the most significant bit by now set 0. And this we can now use to move the 3 remaining bytes into our array. But at what positions? Because we said as well that we want to consider endiness. I will also create for this 2 static const expr values that can be the high byte, and the high byte is when I have little endian then my high byte, the most significant byte, is at position 2, and if not, we push the high byte into the first position. And the same we do for our low byte. But in the opposite, right? So what does this mean? This is, we are defining our index into our array for our most and least significant byte. When we have little endian, then the most significant byte has to be at the end of the array, and if we have big endian, it needs to be at the front. Similar goes for our least significant byte. If we are on little endian, this should be the first one, and if we're on big endian, it should be the last one. And now we can use the information that we learned in the last video and say, okay, the data or the position in the array where the most significant bit goes will be equal to wrap shifted 16 bits to the right. Remember, the first or the most significant byte of the wrap 232 is 0. So we want the third byte, like the second most significant. Therefore, we move 16 bits to the right, which causes the second most significant byte to move 2 bytes to the right, so it becomes the first. And we assign that one to our data, high byte. And the middle one is at position 1, and the middle one will always be also the third most significant byte in wrap 32, right? If we go from left to right, we have, let's say, so the A byte, the A's, they are 0 now in rep 32. The B byte is this one that we move 16 bits. So if we move that 16 bits, then we get this, and we can safely cast it to the unsigned int 8 type because we effectively are already in the range of an unsigned int 8. The middle byte, right, if we will be the one with the CC. So this one we will move 8 bits and our byte becomes BBCC. And this one we cannot cast directly to an int because we have still the B byte, like the second byte, with values. So what we will do, after we shifted the whole thing 8 bytes to the right, we will apply a bitwise AND with 0xFF, which will then turn this into this. It will deactivate or zero out all the bytes that we don't want, and we say we want only the last one, because FF is equal for a 32-bit type to this. Therefore, everything that we have 0 will be 0, and the only bits that we want are the bits of the last byte, and therefore we put FF and get the desired output. Then the least significant byte will be DD. Therefore, we don't have to do any shift. We just apply in the same way the bitwise AND. So we zero out all the other bytes in the rep 32 and are only left with DD. And that's it. For converting back into unsigned int 32, we just do the same thing the other way around. We only don't need the bitwise ANDs anymore. So we will just return our most significant byte and move it 3 bytes to the right, to the left. We OR it with our middle byte that we will move 8 bytes to the left, and finally we OR it with our least significant byte. And that's it. Let's try it out. And what do we want? Let's say we want this crazy number, or let's write it actually as a number. And if we now go to a unsigned int 32 type, we can simply assign it, and we will see that the numbers are equal. Perfect. And we can also see, if we hover now on the U24, that our least significant byte is the last one, and the most significant byte is the first one. We can make this even more visible. Well, let's watch this in the debugger. And we see that our most significant byte, AA, is the last one, and our least significant byte is the first one. Great. We can also perform operations with them. Works very well. The only thing that's not working yet is this, right? We said we will have to override the operations. And let's quickly do this. And we will make our lives easier if we say return this equals this plus other. We do the same for subtraction, for multiplication, for division, for modulo, for bitwise and for bitwise or for bitwise exclusive or left shift and right shift. And now we can see it works. Let's have a look. So AADDBC, and we can see that this works nicely. The only thing that we want to do now is to default the other constructors and the assignment operators. And we should be done. Perfect. I hope you liked it. We will use this class. I promise. We will find a very good use case for it. I hope you liked it, and see you next time. Bye.